Hello everybody, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion on second order ordinary differential equations, ODEs, and in particular we're going to turn our attention to what happens when the coefficients of these second order ODEs are variable, are functions. And so far we've been looking at those equations with constant coefficients, and we found out that there's a general solution process that allows us to arrive at a general analytical or exact solution. Then we compare that to numerical solutions for accuracy and so on. But it turns out that when you make at least one of the coefficients a function, so a variable coefficient, then there's no general procedure by which we can arrive at this general solution. However, there are some specific procedures by which we can arrive at solutions of very specific equations. So that's what we're going to try to do today in terms of an analytical formulation. So modeling methods in ME. And we're going to look at variable coefficient, second order ODEs. So let's write this equation in a general form. We are going to be concerned with the linear version of this equation. So one that looks like this. So notice we're keeping it linear. Obviously, if this equation were nonlinear, then there's even less of a hope to get to a general procedure by which we can solve this equation. But if it's linear, there might be some avenues. And we're also keeping it homogeneous. So this is a linear homogeneous ODE. Okay, so again, there's no general procedure. However, we need to figure out a way of getting at least two answers of very specific equations, because these types of equations would in fact govern a wide variety of problems in science and engineering, from heat transfer to fluid mechanics to all kinds of things. You'll find equations that look like this. And one thing to note is that I've now expressed this equation in terms of x rather than expressing it in terms of t, rather than expressing this as an initial value problem, or I'm leading towards a boundary value problem, because in most cases where we'll find a physical application for these equations, they will appear to be boundary value problems. So let's just connote these formulation today in terms of boundary value problems. So again, to reiterate, there isn't a general methodology that guarantees a solution of these types of ODEs. Right? In general, the only thing that we can expect a solution in the form, so whatever the solution is and whatever the procedure or the method to get us there, we can expect the solution to be sort of like a combination of two functions, f and g, right? Separated by two constants of integration, because this is a second order equation, and therefore there's an implicit integration or double integration that would lead us to the answer. So again, this is the only thing that we can infer about this equation. There's no general procedure. A solution of an equation or procedure to solve an equation will depend entirely on what those functions p and q look like. Now there's one specific variable coefficient second order linear homogeneous ODE known as the Euler-Cauchy equation, has a simple solution approach. So that's an equation that looks like this. is x squared, the second y dx squared, plus a times x dy dx, plus b y of x is equal to 0. Again, this is a variable coefficient, as you can see. There's two coefficients that are functions of x. Second order linear homogeneous equation. If we write it in this general form, we can very easily infer that the function p of x is a divided by x, and the function q of x is b divided by x squared. So we're basically dividing everything by x squared, and that's how p and q will end up. But that's immaterial, because basically what would happen is that if the equation looks like this, and notice that there's a trend to this equation, we have a second order polynomial accompanying the second order derivative, the first order polynomial, a polynomial with the first order derivative, and a zeroth order polynomial with the zeroth order derivative. So if the equation happens to look this way, then we can attempt a trial solution. So try a solution y1 of x, and we're going to call it y1 because it's not the only solution, as you'll see in a minute. It's a trial solution. And if we try a solution x to the m, so we're going to see if x to the m works here. Let's try and see if that works. Then the derivative of y1 with respect to x will just be m times x to the m minus 1, and the second derivative will be m times m minus 1 times x to the power of m minus 2, and so on and so forth. So I can take as many derivatives of this polynomial, which may not be a polynomial because m might not be an integer number, so it might be a rational function. But whatever it is, I'm going to attempt a solution of this form, and then I'm going to use these derivatives and plug them back into the differential equation. So plugging back into ODE leads to, so if we plug these back into the ODE, we'll notice that in order to arrive at a non-trivial solution, we'll get an equation that looks like this, and this is again called an adjoint equation. So in order for the solution not to be trivial, not to be 0, this will have to be true. So for a non-trivial solution. So that means that this is, as you can see, a very simple quadratic equation for m, which has two solutions. So minus b plus minus the square root of b squared minus 4ac, which is minus 4b, divided by 2a, which is 2. So those are the roots of this equation, and those are the values of m on this trial solution that will make the solution to this equation, or the trial solution, a non-trivial one. Now, the solution itself will depend on the nature of these roots. So if m1 and 2, let me go back here. So if m1 and m2 are real and different, then y of x is equal to c1, one constant of integration, times x to the m1, plus c2, another constant of integration, times x to the m2. So there's a superposition of the two possible solutions. So there's one general solution. The constant c1 and c2 can be found by imposing the boundary conditions or the initial conditions if this were a function of time. 2, if m1 and 2 are real and repeated, that is, whatever's the argument here inside the square root is equal to 0, then the solution would look like the following. So y of x will be c1 plus c2 times the log of x, and all of these times x to the m, such that m is equal to m1, which is equal to m2. It's a repeated real root. So here's the other possibility. And obviously there's a third possibility for what the solution m1, m2 can be. and those are if the argument is negative, and that is going to yield if M1 and 2 are complex. And in this case, we're going to let M1 and M2 be a real part alpha plus minus an imaginary part beta. And again, always the complex roots of a quadratic equation are conjugate, so one is a plus and a minus of the imaginary part. So the solution in this case will be x to the alpha times c1 times the cosine of beta times the log of x plus c2 times the sine of beta times the log of x. Notice that the argument of these trigonometric functions is a logarithm. So this is the third option for the solution of the Cauchy or the Euler-Cauchy equation. Again, this is a very specific equation. It might be applicable in some cases to some physical phenomena. And heat transfer, for example, it may appear in some fin problems, and heat transfer extended surface problems with fins of a very specific shape can lead to this equation. So again, this is just one example of a variable coefficient ordinary differential equation, but this is essentially the only one that leads to a simple solution like this. Now, in general, variable coefficient second order ODEs require a more involved procedure to arrive at general solutions. And again, I've already said this, but this is reiterating, and that would depend on what the functions P and Q look like. So one of the solution methods to do this is called a series solution method for, again, second order variable coefficient linear homogeneous ODEs. So given what we started with, the second order ODE denoted by the two variable coefficients, which could be variable, which could both be variable, or basically just one of them could be variable. And in fact, if none of them are variable coefficients, if they happen to be constant, both of them, then whatever solution method that we find, we should revert back to the general solution method of constant coefficient ODEs. So it should be a generalization of the constant coefficient method. So we're going to assume that Px and Qx are non-singular, unlike the Cauchy-Euler equation, because remember in the Cauchy-Euler equation, or Euler-Cauchy equation, these actually are singular functions. So this one's singular at x equals 0, and this is doubly singular at x equals 0. However, for this series solution method to apply in general, these have to be non-singular, continuous functions. So we're going to try a solution y of x in terms of a Taylor series. That is, we're going to let y of x, which is a solution that we're seeking, be equal to the summation from n equals 0 to infinity of some coefficient Cn times x minus x0 to the power of n. We know that x0 is the expansion point, which is an arbitrary point that we decide where we're going to define or write these polynomials about. This is an infinite series of polynomials of infinite order from 0 to infinity. And these are coefficients that we know where to find if we knew the function y, whatever the original function y is. We know that the coefficients are the nth derivative of y evaluated at the expansion point. So remember that Cn is equal to 1 over n factorial times the nth derivative of y with respect to x to the n, evaluated at the expansion point x0. So we know what those coefficients are. However, we cannot determine those coefficients because we don't know what the function y is. It's precisely what we're looking for. So we're essentially deciding, well, I don't know what y is, but I'm going to say it is a Taylor series. I know that that's true for a fact because I know that I can take any function I want, including a function that I don't know, which is a solution to this equation, and expand it like this. And that will be an exact expansion, an exact representation of the function. So we could somehow manipulate these series so that the final solution looks like the following. So y of x is equal to some c0 times f of x plus some c1 times g of x, which we said originally is the only thing that we could say about the solution. Whatever the solution process is going to lead to a solution of this form because there are two implicit constants of integration because this is a second order equation, right? So somehow we're going to take this form that we're going to figure out and we're going to place it in terms of these, or we're going to rewrite it so that it looks like this. It seems like a monumental task because if you think about it, we're arbitrarily saying that the solution of this equation is this series, right? And we can decide what x0 is the expansion point, so we can make it 0 if we want to. However, we have an infinite number of coefficients Cn to determine. So that's very difficult to do. And somehow we're going to take infinite coefficients. We're going to take infinite minus 2 coefficients and put them in terms of the first two, of C0 and C1. Somehow we're going to try to do that, and somehow it works out. So I'm going to give you an example. A very simple example. So given the second derivative of x with respect to x squared plus y of x is equal to 0. So this is a constant coefficient equation. We can find the roots of this equation and we'll find plus I and minus I. So these are imaginary roots. And so the solution of this equation, y of x, is the cosine of x and the sine of x. Okay, C0 times the cosine of x, C1 times the sine of x, or vice versa. C0 times the sine and C1 times the cosine. That really doesn't matter. So it's the sine and the cosine. We know this because we know how to solve constant coefficient ODEs. But let's see if we can actually use this approach to get to the same answer. It seems strange that we would get to the same answer using these polynomials instead of a general approach. So if you note, the first thing is that Px is equal to 0 and Qx is equal to 1, right? So if we recast this equation in terms of the general form like this, the variable coefficient Px is not a variable coefficient, it's in fact 0, and the variable coefficient Qx is not a variable coefficient, it's in fact 1. So this is obviously a constant coefficient, ODE. So we're going to let y of x be equal to the summation from n equals 0 to infinity of Cn times x minus x0 to the power of n. And I would say, let's just keep it x0 and c0, but and I'm going to, actually for simplicity, I'm going to make the expansion point equal to 0. Okay, I'm going to arbitrarily decide that that's the case. So if that's the case, and I want to try to find the Cn coefficients, at least infinite of them minus 2, except the C0 and the C1. So I'm going to say if y of x is equal to the summation from n equals 0 to infinity of Cn times x to the n, then dy dx is equal to the summation from n equal 1 to infinity of Cn times n times x to the n minus 1, right? And now the summation needs to start at n equal 1, obviously, because the 0th order term becomes 0. We cannot start at 0 because then we'll have an x to the minus 1 in the series. And the second derivative of y with respect to x squared is, well, the summation from n equal 2 to infinity of Cn times n minus 1 times x to the n minus 2. Okay. And what we're going to do is that we're going to plug these back into the ODE. We're going to take these three and plug them in here, actually only two of them, the second derivative and the original function, to see what happens. So plug back into ODE, and then I'll have summation from n equal 2 to infinity of Cn times n to the minus 1 to n minus 1 times x to the power of n minus 2 plus the summation from n equals 0 to infinity of Cn times x to the n is equal to 0. Okay, that's what I have. So what I'm going to do now is shift these index n so that I can make the powers be exactly the same, so I can combine the two series. So I'm going to shift index of first summation so that m is equal to n minus 2. So I'm going to replace n minus 2 by m, right? And therefore, n is equal to m plus 2. So if that's the case, the first summation is going to be from m equals, so when n is equal to 2, m is equal to 0, from 0 to infinity, of Cm plus 2 of m plus 2, m plus 2 minus 1, and x to the power of m. N minus 2 is equal to m. So I basically shifted just the notation, the index. I didn't move anything, I just replaced m with n minus 2. So this yields exactly this. And the second one I'm going to leave as is. Right? So then I'm going to switch the notation back to n. So switch back from m to n. Right? So this is a series from n equals 0 to infinity of Cn plus 2, n plus 2, n plus 1, x to the n, plus a summation from n equals 0 to infinity of Cn times x to the n is equal to 0. And now I can combine the two series. So combining, because both start at 0 and both include the same power, x to the n. So I can combine these two series as a single one, the summation from n equals 0 to infinity, Cn plus 2 times n plus 2, n plus 1, plus Cn times x to the n is equal to 0. Alright, so I now have the first clue. Because in order for this solution not to be trivial, right, the only thing that can be 0 out of this summation, so notice that the summation of all these numbers is equal to 0, right? Either x to the n is equal to 0 or these numbers equal to 0. So for a non-trivial solution, so Cn plus 2 times n plus 2, n plus 1, plus Cn should be equal to 0. That's the only thing that can be 0 here, not this. And if this is the case, then I can write these as Cn plus 2 divided by Cn is equal to minus 1, n plus 2, n plus 1. So what I have now is a so-called recurrence relation. So a relation that relates an equation that associates two coefficients every two positions. So it relates C2 to C0, it relates C4 to C2, it relates C6 to C4. It also relates the odd ones. It relates C3 to C1, C5 to C3, and so on, right? So this means that we only need to know C0 and C1, and we can relate all the other ones, all other ones, to C0 and C1. It's very simple. So for n equals 0, we have C2 over C0 is equal to minus 1 divided by 2 times 1, so minus 1/2. So that leads to C2 is equal to 1/2 of C0, or minus 1/2 of C0. For n equal 2, I have C4 divided by C2 is equal to minus 1 divided by 3, and divided by 4 times 3, so minus 12, minus 1/12, right? And then I can take this first relationship, the one that relates C2 to C0, and I can replace it here, and then I will find out that C4 is related to C0, so the ratio of C4 to C0 is positive 1 over 24, because I've taken C4, I've taken C2, which is minus 1/2 of C0, and I've replaced it here, and then the 1/2 goes to the right hand side, and I have positive 1/24. Then I can continue. So at n equal 4, C6 divided by C4 is equal to minus 1 over 30. And then I can take this relationship of C4 and C0, plug it in here, and it will be 1/24 times 1/30. And then therefore C6 divided by C0 is minus 1 over 720. So then I have an alternating sign, minus 1/2, 1/24, minus 1 over 720, and so on and so forth. And I can continue as many times as I want. Similarly, I can do this for the odd terms. I can say at n equal 1, C3 over C1, again with this recurrence relationship, C3 over C1 is equal to minus 1 times, or divided by 3 times 2, so minus 1/6. So it's equal to minus 1/6. Then at n equal 3, C5 divided by C3 is equal to, so when n is equal to 3, I have 5 times 4 is 20, minus 1/20. Minus 1/20. So then I can take C3 over C1 and plug it in here, and that leads to C5 over C1 is equal to 1/20 times 1/6 is the positive 120. And I can continue to n equal 5, so C7 divided by C5 is equal to minus 1 over 42. And then I can replace C5 with this relationship with C1, so then C7 by C1 is equal to negative 1 over 5040. And so on and so forth. So I can do all infinite one of them, and you can see that they all actually come back to C1. So all the even coefficients relate back to C0, all of them, and all the odd coefficients relate back to C1. So that's precisely what we're looking for. So if we say that the solution that we propose y of x, which was simply the summation from n equals 0 to infinity of Cn times x to the n, is such that somehow it can be written as f x times C0 plus gx times C1, then what I'm going to do is I'm going to collect these two sequences together. So one looks like C0, the other one looks like C2 times x to the 2, the other one looks like C4 times x to the 4, plus C6 times x to the 6, so on and so forth. And the other looks like C1 times x plus C3 times x cubed plus C5 times x to the 5 plus so on and so forth. Oops, sorry. So this is what these series looks like, right? Some even terms and some odd terms. Very simple. But I know that these even terms are all related to C0, right? I know that C2 is related to C0 this way. I know that C4 is related to C0 this way, and C6 is related to C0 this way. So technically, I can just take C0 as a common factor outside and say that this is 1 plus C2 over C0 times x squared plus C4 over C0 times x to the 4 plus C6 over C0 times x to the 6 plus so on and so forth, plus I can also take C1 outside times x plus C3 over C1 times x to the 3 plus C5 over C1 times x to the 5 plus C7 over C1 times x to the 7 plus so on and so forth. Infinite number of them. Okay, so all the evens and all the odds. And then I know what this is. This is just the number. So y of x, keep inferring this, so y of x is then equal to C0 times 1 plus minus 1/2 times x squared plus 1/24 times x to the 4 plus minus 1 over 720 x to the 6, and you can continue finding out what those numbers are very simply, plus C1 times x plus minus 1/6 times x to the 3 plus 1 over 120 x to the 5 plus negative 1 over 5040 times x to the 7 plus an infinite number of odd terms, right? So this is a function, and this is a function. This is a well-defined function. There's no coefficients in there. This is a well-defined function. There's no coefficients in there. They're all multiplying C0 and C1. It just happens that if I do some deduction here, it turns out that I can relate this to, so notice that there's an alternating sign here. 1 over 2 is 1 over 2 factorial, 1 over 24 is 1 over 4 factorial, 1 over 720 is 1 over 6 factorial. So this can be 1 over 0 factorial plus minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the 4th plus minus 1 over 6 factorial x to the 6, and I can continue to write that in this very simple form. It just happens to be this way for this particular equation. Plus C1, I can write this as 1 over 1 factorial times x plus minus 1 over 3 factorial times x to the 3 plus 1 over 5 factorial times x to the 5 plus minus 1 over 7 factorial, which is 5040, times x to the 7, and so on and so forth. Right? So I have these series that are perfectly defined, each multiplying each other by C0 and C1, right? Just now I have the solution in terms of just two constants of integration. And it turns out that if you expand the cosine of x and the sine of x in Taylor series, you will obtain exactly the coefficients above. So this right here is perfectly analogous to say C0 times the cosine of x plus C1 times the sine of x. So that is the answer to this differential equation, which, by the way, we knew all along, because this equation, remember, is a constant coefficient equation. All the way 3 pages ago. This is a constant coefficient equation that we can very easily solve by the method that we already learned a couple of classes ago, or back when you took differential equations, that leads to a general solution in terms of a cosine and a sine. And these happen to be exactly these forms right here. If you take a cosine and expand it in terms of a Taylor series, remember the coefficients are the derivative of these divided by n factorial, the derivative of these evaluated at x equals 0 times the third derivative, the fourth derivative, the fifth derivative, and this is a cosine and this is a sine. All right, so it works out. So we found through a series approximation of the solution that the answer is exactly what we expected, cosine and sine. So similarly, we can do the same with another version of the equation. So similarly, we could attempt a series solution of the second derivative of y with respect to x squared minus y of x is equal to 0. So that's almost identical to the previous equation, but instead of having a plus, it has a minus, and this is a constant coefficient equation, so the variable coefficient px function is equal to 0 in this case again, and qx is equal to minus 1, so these are constant coefficients. So when we attempt the solution of this constant coefficient differential equation using a regular method that we learned before, we'll find that, well, we have real roots, and those real roots are non-repeated. They're different. One is plus 1 and the other one is minus 1. So we get a solution in terms of, the solution of these constant coefficient second order ODE should be either a times e to the x plus b e to the minus x, right? So we have the solution in terms of exponentials, one with the root positive 1 and the other one with the root negative 1, or we can also express this solution in terms of cosine hyperbolic of x plus d equals to the sine hyperbolic of x. Same thing. So recall that such that the cosine hyperbolic of x is defined as e to the x plus e to the minus x divided by 2, and the sine hyperbolic of x is equal to e to the x minus e to the minus x divided by 2. Okay, that's the definition of the cosine hyperbolic and the sine hyperbolic. They're just basically exponential functions. So basically, following the series approach, that is the one that says let y of x equals to the summation from n equals 0 to infinity of Cn x to the n, right? Then take the derivative of that, take the second derivative. We'll find a recurrence relationship that looks like Cn plus 2 over Cn is equal to 1 over n plus 2, n plus 1. This is pretty much the same one as before, except that it has a positive sign. Instead of a minus 1, it has a 1. So this is a recurrence relation. So leading to a solution, y of x. Do the whole analysis the same way we just did it. We'll find 1 over 0 factorial plus 1 over 2 factorial times x to the 2 plus 1 over 4 factorial of times x to the 4 plus 1 over 6 factorial times x to the 6, so on and so forth. And then all the odd terms is x, or 1 over 1 factorial times x plus 1 over 3 factorial times x to the 3 plus 1 over 5 factorial times x to the 5 plus 1 over 7 factorial times x to the 7 plus so on and so forth. As you can see, there is no alternating sign, and basically this is identical, equivalent to y of x is equal to c0 times the cosine hyperbolic of x plus c1 times the sine hyperbolic of x. This is perfectly equivalent to this, which verifies that the solution looks like this. You can try it yourself. You can take the cosine hyperbolic of x and try to expand it in terms of a Taylor series. So differentiate it n times, differentiate it and evaluate it at x equals 0, and then evaluate it at x equals 2, at x equals, take the second derivative, evaluate it at x equals 0, take the third derivative, evaluate it at x equals 0, the fourth derivative, and so on and so forth. And then this is exactly what you're going to find. You're going to find that all the odd terms vanish, because all the odd derivatives will give you sine hyperbolic, and the sine hyperbolic at x equals 0 is always equal to 0, so they will vanish. And all the other ones will just give you 1. And all you end up is with the denominator. Same for the sine hyperbolic, right? The sine hyperbolic at x equals 0 is equal to 0. But when you differentiate it once, you get the cosine hyperbolic, which at x equals 0 is equal to 1. The cosine hyperbolic, then when you differentiate it again, it will be the sine, so that will vanish. So all the even terms will vanish, and the Taylor series expansion of the sine, and all the odd terms will actually remain. So this function right here is perfectly equivalent to the cosine hyperbolic, while this function right here is perfectly equivalent to the sine hyperbolic. So this is another demonstration that this is in fact the solution of this equation. All right. Now, I kind of cheated here because we're trying to solve variable coefficient equations, and we're basically solving constant coefficient equations, which we already know how to solve, analytically at least. So what if these functions p and x, or p and q, are actual functions? So if px and qx in the equation are singular, then the power series, so the Taylor series solution, is only valid from the expansion point to the nearest singularity of px and or qx. Okay, that means that there's a radius of convergency for Taylor series. Taylor series are not always exact. They're exact as long as the function that you're trying to expand is perfectly well behaved, like the sine, the cosine, the cosine hyperbolic, the sine hyperbolic. Those are smooth functions. But if you try to expand the tangent of x, right, the tangent of x, you know, is singular at x equal pi over 2. So what happens is that if you try to expand it into a Taylor series and your expansion point x0 is equal to 0, the solution will only be valid from 0 to pi over 2. It will only be valid from the point of expansion to the point of near singularity. After that, your series solution is no longer equivalent to the solution, to the function that you're trying to expand. So we're going to use these to attempt the following. Let's look at an example of a very relevant equation that looks like this. Minus 2x dy dx plus nu plus 1 y of x is equal to 0. Okay, so that strange looking equation is called the Legendre's equation. Legendre's equation. Okay, you can come up with your own equation or just add your coefficients there, just arbitrarily. However, this one is not an arbitrary equation. This is an equation that has relevance because this equation arises from the solution of partial differential equations PDEs, which we're going to see in the next part of the semester, in spherical coordinates. Alright, so when you're trying to solve partial differential equations in spherical coordinates, you do something called separation of variables. So you break up the equation into the different independent variables, r, theta, and phi, and then you do a transformation in one of those dimensions, and you end up with an ODE that looks like this. And that's why this equation is so relevant, because obviously the solution of PDEs in spherical coordinates is very important. There's a lot of phenomena, many phenomena in engineering and science that propagate spherically, like sound, for example, like light, like heat, like all kinds of things propagate spherically. So it is important that we know how to solve these equations in spherical coordinates. And then once we break it up, we know how to solve the individual equations that arise from this. So when we rewrite this equation, we get the following. The second y, the x squared, minus 2x divided by 1 minus x squared, dy dx, plus nu plus 1 minus x squared, times y of x is equal to 0. And this right here is p of x, well this right here is q of x. And you can see that p of x and q of x are singular at x equal plus minus 1. So they all become singular, this function p and this function q, when x is equal either 1 or minus 1. Alright, so we can plot these functions. These functions p and q, I'm going to squeeze them here. I can plot them right here. This is y. And so this is x. Here's 1, and here's minus 1. So this is minus 1. And this is 1. And I can plot p of x, and p of x is going to look like this. So as you can see, it goes singular here at x equal minus 1 and singular here at x equal 1. So this is p of x. And I can plot q of x, and I would also go singular here. And this is p of x. I'm sorry, q of x. Alright, I sort of drew this not in scale, so you get the point. This is where the asymptote is. So we can try a series expansion about an expansion point x0 equals 0, because that's not a singularity. And we know that if we try an expansion point x0 equals 0, the solution y of x that we find will only be valid between -1 and 1. That's it, because that's the point to the nearest singularity. So if we say y of x is equal to the summation from n equals 0 to infinity of cn x to the n, and likewise dy dx at x is equal to the summation from n equal 1 to infinity of cn times n times x to the n minus 1, and the second derivative of y with respect to x squared is then the summation from n equal 2 to infinity of cn times n minus 1 times x to the power of n minus 2. So I have the three solutions, which I am then going to plug into the original Legendre's equation, either here or here, it doesn't make any difference, right? So back into ODE, then I have 1 minus x squared times the summation from n equal 2 to infinity of cn n minus 1 times x to the n minus 2 minus 2x times the summation from n equal 1 to infinity of cn n x n minus 1 plus nu times nu plus 1 summation from n equals 0 to infinity of cn times x to the n is equal to 0. So that's now the new differential equation. And hopefully then I can find a recurrence relationship between cn's, the even terms and the odd terms. So in order to do that, I'm going to go about exactly what I did before. So I'm going to switching indices of the second summation and third summation, then I will find the following. And in addition to that, I'm going to have to do some manipulation of the series, because even after I switch these n to n minus 1 and this n to n minus 2, and I multiply things over here, and you notice that there's an extra x here, that when I multiply times x to the n minus 1, it will be x to the n, right? So then I'm going to have to take some terms out of some of these series, and at the end of the day, you can do this yourselves, but this is going to look like this. It's going to be 2c2 plus nu plus 1 times c0 plus 6c3 plus nu times nu plus 1 minus 2. This is a minus times c1 times x plus a single summation from n equal 2 to infinity, where I have cn plus 2, n plus 2, n plus 1, minus cn times n minus 1, minus 2 cn times n, plus nu times nu plus 1 times cn, x to the n is equal to 0. So that's the overall differential equation now. And that produces three recurrence relations. So the recurrence one is very simple. One relates C2 to C0, as you can see. The first one, C2 divided by C0 is well, I can solve for these. It's minus nu plus 1 divided by 2. So that is the first recurrence relation. The second recurrence relation is C3 divided by C1. I can solve for C3 in terms of C1 here. Is equal to 2 minus nu plus 1 divided by 6. And the third recurrence relation, I can place Cn plus 2 in terms of Cn. I can collect all these Cn's together. And I can say that Cn plus 2 divided by Cn is equal to minus nu plus 1, n, or plus n times n plus 1, is divided by n plus 1, n plus 2. And in fact, if you make n equals 0, for example, you'll find exactly this. If you make on this third recurrence relation, should actually be a generalization of these two. For n equals 0, you have C2 over C0 equals to minus nu times nu plus 1. This one goes away, and then you get 2 in the denominator, which is exactly this. At n equal 1, you get C3 over C1 of 1 times 2, which is 2, minus nu times nu minus nu plus 1, which is this, and this is 3 times 2, which is 6. So there you go. These two initial recurrence relationships, which come directly out of these, is just a particularization of this general one for n equal 1 and n equal 0. So basically, the solution y of x can be written in terms of C0 and in terms of C1, the same way we wrote the solution of the previous problem. So this will be 1 plus minus nu times nu plus 1 divided by 2 factorial times x squared plus minus nu times nu plus 1, 6 minus nu plus 1 divided by 4 factorial times x to the 4 plus so on and so forth. And then you can use the odd relationships, plus C1 times x plus 2 minus nu plus 1 divided by 3 factorial times x to the 3 plus 2 minus nu times nu plus 1 times 12 minus nu times nu plus 1. All of these divided by 5 factorial times x to the 5 plus in close bracket. So all possible odd terms. So yeah, so obviously this looks a lot more complicated than the sine and the cosine, or the cosine hyperbolic and the sine hyperbolics, which just basically has alternating signs, and then it has the factorials on the denominator, and this will be 1 or minus 1. Very easy to do. In this particular case, they look slightly different. Plus you have the term nu there, which is just the coefficient of the original equation. The original Legendre equation has that coefficient nu, which comes, by the way, from that substitution of one of the dimensions in spherical coordinates, as you will see later in the semester. But in essence, what happens is that these particular functions right here, which are just Taylor or power series of infinite power, they are just functions, and they're already pre-programmed for you. If you just go to MATLAB or MathCAD or Mathematica or any mathematical spreadsheet, even Excel, if you add the mathematical module to it, you'll have the ability to evaluate these functions, and these functions are called Legendre functions. So y of x is equal to C0 u nu of x plus C1 v nu of x. So these function here with even terms is called the u function, and these function here with odd terms, or odd coefficients, or odd powers, are called the v functions. And these are u and v such that u nu and v nu are the Legendre functions of the first. So u is the Legendre function of the first kind, and the second kind. So u is the Legendre function of the first kind, v is the Legendre function of the second kind, of order nu. There's an order to these functions, and it's called the order nu. So these are just basically like the sine or the cosine, or like the logarithm, like the exponentials. These are functions which you need to evaluate implicitly using these embedded functions in mathematical spreadsheets. But you can just basically evaluate Legendre functions. Just go to the help section of any of these mathematical spreadsheets, and you'll be able to see that you can evaluate without the need of you programming this infinite series right here. Which, by the way, notice that these infinite series have denominators of increasing factorial order, which means that larger powers actually tend to vanish, right? Also, more importantly, is that remember that this solution is only valid between x equal -1 to x equal 1. So x will always be less than 1 in terms of magnitude. So larger powers of a number less than 1 will always give you a smaller number. So numbers of larger power here will actually tend to vanish, are negligible compared to these numbers of lower power. So you can approximate these Legendre functions very easily. Now, it turns out that if nu is either equal to 0, 1, 2, 3, or any integer, so if the original nu on the Legendre equation right here happens to be an integer, so say for example this number is 6, then that means that nu is equal to 2. So 2 times 2 plus 1 is equal to 6. So if this equation is written as 6y, then you know that nu is an integer, nu is equal to 6. But if this is 7y, then nu is not an integer. You cannot factorize an integer out of that. But it turns out that if nu is an integer, then these infinite series terminate both the even and the odd, and we can retrieve the so-called Legendre polynomials. Pn of x and Qn of x, such that the solution y of x will be in terms of these Legendre polynomials, C0 and C1 of Qn of x. So instead of being this infinite power functions, they're just simply polynomials, right? So it turns out that the P0 of x is equal to 1, P1 of x is equal to x, P2 of x is equal to 1/2 of 3x squared minus 1. P3 of x is equal to 1/2 of 5x cubed minus 3x, so on and so forth. So there's a recurrence relationship between these polynomials with recurrence relation such that n plus 1 times Pn1 or Pn plus 1 of x is equal to 2n plus 1 times x Pn minus n Pn minus 1. So I can relate the third order polynomial to the first order, to the third order to the second order and the first order, right? I can relate the fourth order to the second order, to the third order and the second order, and so on and so forth. So I can always find the next polynomial by looking at the two previous ones. So this is a Pn of x, and this is Pn1 of x. So this is a recurrence relation for the Legendre polynomial of the first kind, Pn of x. Also, something very important is that these polynomials satisfy the orthogonality condition, which will be extremely important later on in the semester because we will make use of it to be able to find non-trivial solutions. And an orthogonality condition basically means that these polynomials are orthogonal to each other. Polynomials of different order are orthogonal to each other, while polynomials of the same order are not. So the integral from -1 to 1 of a polynomial of order n and a polynomial of order m, when multiplied together, will give you either 0 if m is different than n. So if the two are of different order, you get 0. And you only get a non-zero answer if m is equal to n. That is the orthogonality condition. In this case, the solution is 2 divided by 2n plus 1, which is irrelevant right now. But the point is that you can do an infinite number of these integrals of different order polynomials. You can integrate the polynomial of order 5 and the polynomial of order 7, and you'll get 0. But if the two have the same order, then you get a number different than 0. That's the orthogonality condition, which will be relevant later on. But for now, let's just keep it here as a side note. Now I've defined the polynomial p, which is a polynomial of the first kind. Also, the polynomial of the second kind, q0 of x is equal to 1/2 of the log of 1 plus x divided by 1 minus x. So this is not a polynomial, as you can see. It's an irrational function, and it's not well behaved. It's singular at x equals 0, at x equal 1. I'm sorry. Q1 of x is equal to x over 2 times the log of 1 plus x divided by 1 minus x minus 1. Q2 of x is equal to 3x squared minus 1 divided by 4 times the log of 1 plus x, 1 minus x, minus 3x over 2, and so on and so forth. So these are singular. Qn of x is singular at x equals plus and minus 1. As expected, because remember the original equation had a singularity at x equal 1 and at x equal minus 1. And we said that the solution, whatever it is, the solution of these equations, would only be valid between x equal 1 and x equal minus 1, because that's the radius of convergency of the original Taylor series that we propose as a trial solution to this problem. So the final solution of the Legendre's equation goes like y of x is equal to c0 u nu of x plus c1 v nu of x if nu is not an integer, or y of x is equal to c0 times pn of x plus c1 times qn of x if nu is equal to some n, which is equal to an integer. If the original function that is given to us turns out that can factorize to nu being equal to an integer. So that is the solution of the Legendre's equation. And again, that has very special relevance because it turns out that it's the only way that we could get analytical solutions for 100 years or so to equations in spherical coordinates, okay, to a very particular dimension in spherical coordinates after a transformation, after separation of variables and transformations. Now with numerical solutions, we can get around this and find an approximation to the solution that matches these. And again, these so-called Legendre functions of the first kind and the second kind of order nu, or Legendre polynomials of the first kind and the second kind of order n, are just functions that are pre-programmed in mathematical spreadsheets that you can just simply tab in. Like you would say, what is the sine of 3? You get an answer. You can ask, what is u sub 3 of 4? And you get an answer. So again, this is something that is relevant, not only relevant in the solution of these types of equations, but also relevant in statistical analysis, which we will not cover in this class, but so that's for your information. So this is all I wanted to go over today. Again, it's completely analytical, but we'll get a chance to kind of exercise some of these during our live sessions. So thank you for your attention, and I'll see you next class.